Hello. Yeah, I'm going to talk about TLS today, and a quick introduction of myself. I mean, Markus already said that I work as a freelance journalist and usually write about IT topics and IT security topics for Golem, but also sometimes for newspapers like the Taz or Zeit Online. Also, I try to find and fix security vulnerabilities in free software products. I run a project which is the Fuzzing Project, where I use fuzz testing to find bugs, which is funded by the Linux Foundation's Core Infrastructure Initiative. And I write a monthly newsletter about TLS. So why do we talk about TLS? We're using TLS all the time. Basically, I think every one of you has probably used TLS today in some way or another, like by doing a Google search or logging into your Facebook account or checking your emails, hopefully. This is what happens if you don't use TLS. Like here, a journalist writes, I got hacked mid-air while writing an Apple FBI story. So he was logged into the Wi-Fi and someone else read his emails. So what was happening there is that he was using an email account from a provider called Earthlink, and it seems they don't support TLS for sending emails. So this is bad, and then this happens. So we should care about TLS. Just to get this out of the way with the terminology, so there's many people still say SSL and TLS, so why these two terms? It's actually relatively simple. SSL is just the older version. It was developed by Netscape in the 1990s, and then at some point it was standardized by the IETF, and then it was renamed to TLS. So this is a bit confusing. We have SSL version 2 and SSL version 3. And then it was renamed to TLS, and the versioning started from 1.0. So TLS 1.0 is newer than SSL version 3, and now we have, and TLS 1.2 is the latest, and TLS 1.3 is currently developed. And this I stole from someone else. The colors just indicate like SSL version 2 and version 3 are completely insecure, broken, and SSL 2 is even so broken that it can be a risk even if you're not using it just by providing it, which was research that involved people from this university. TLS 1.0 and 1.1, they are kind of sort of, you can do it in a secure way, but it's really hard and you probably should not use them. And TLS 1.2 is still mostly okay if you use the right modes. Yeah, and TLS 1.3 hopefully will also be okay. And now we had a lot of attacks in the past years. Yeah, here's a long list. I started with Beast, Crime, Breach, Lucky 13, up until Drown. What we can see here is that now you need a fancy name for your attack. And preferably you should also have a logo. So else your attack is not really interesting. But apart from the joking, I mean, what this tells you is there's just a lot more research happening on these issues. Like, if you look back into the past, there were TLS was kind of not a lot of people have looked deeply into this, and now a lot of things come up because just more people are looking at it, and it's a more interesting research target. Now, this slide should give you some thinking. There on the left side, I have attacks that were described at some point in the past, and on the right side is newer attacks that were based on these older attacks. And what we can see here is that many of these attacks we're seeing today, like Drown or like Beast, they're based on much, much older weaknesses that were already known a long time ago. So we knew since 1992 that DSA has some problem with random numbers, which broke the PlayStation 3 protection and also broke several routers on the internet. We knew since 1996 that MD5 is problematic, and then in 2012 the Flame malware used this MD5 weakness, and many similar examples. And also maybe you know these two because they involved researchers from this university. Drown, which was published in January, which is based on a very old attack from Daniel Bleichenbacher, and the invalid curve attack, which is the idea that you can send some points that are not on the elliptic curve that they should be, and then you can turn this into an attack which also is based on a very much older. So what you can take away from this is, especially if you want to do research in this area, then have a look at some very old attack and think about how this can be adapted to modern systems. And it also kind of tells us that we're not very good at fixing these attacks because, yeah, if something is, we already know in 1992 that it's bad, and then in 2012 it becomes a problem again, something is not right. So we're not good at properly fixing these weaknesses. And I want to go to the full history of one such attack. And that's the padding oracle, which the original paper was from Sergey Vodny at the Eurocrypt conference in 2002. And if you cannot follow me, then please ask questions because I want you to really understand what this is about. So we need a bit of background for this attack. So when we're doing TLS, at first we do a handshake, which is not part of this attack. And then both parties have a shared key or several shared keys, and then they communicate with some encryption modes. And what usually was used until quite recently was AES in the so-called CBC mode, plus an HMAC authentication. And that's an important aspect of TLS, that it's actually not just encryption, it's also authentication, which means not only your data is secret, but you're also getting a guarantee that nobody can modify that data on the transmission. And what this, and the crucial thing is here how these two things are combined. And it's using something in the order MAC, then PAD, then encrypt. So what is happening? We have a plain text, and then a MAC is calculated. So the MAC means that guarantees us that there's no modification in it. It's kind of a stamp that guarantees us this data is correct, that's protected by the MAC. So we can verify with the key that this data is correct. Then some padding bytes are there. This is because we have a block cipher that only encrypts blocks of a certain size. So we need to fill it up with some bytes that we have this block size. And then this whole thing is encrypted. And this is how this padding looks like. It's actually just always we have a number, and the number of padding bytes is 1 byte more. So if we have 0, we have 1 padding byte. If we have 1, we have 2 padding bytes, 3 padding bytes. And it goes up to 16. Crucial here is that a single 0 byte is the smallest valid padding. And then we have error codes. And the crucial thing here is that there are different error codes depending if the padding is wrong or if the MAC is wrong. So if the MAC is wrong, we get a bad record MAC error. And if the padding is wrong, we get a decryption failed error. At least that was the case in these older TLS standards. And this is the CBC mode, the decryption part. Now, don't get scared if this looks too complicated. What is important here is that the encrypted text gets XORed into the next block. What this means is an attacker can change the encrypted text, and it will create a change in the next block in the plain text when it's decrypted. So what our attacker can do is now we're throwing away the last block because we're not interested in that because that's only padding and MAC and we want to decrypt the data. We're not interested in the MAC or the padding. And then we're XORing from this block the last byte with a value that we're guessing which value it might be. And then if we guessed right, then we have a 0 here. And a 0 is a valid padding. So if we get a MAC error, we know the padding is valid. Therefore, we can just try all possible values for this byte. And when we got the right one, we get a different error message. And then we can do the same for the next byte and the next and the next and decrypt everything. Okay. Now, the first fix for this was that just get rid of this second error message and always send the same error message. And now the latest TLS standard says that the decryption failed error must not be sent. Okay, so this was 2002. So we assume everyone has fixed this, right? Except some people, like this is a Züxel Unified Security Gateway. So I recently did with someone together, we made a project where we did an internet-wide scan for this very old vulnerability in its original version. And we found a number of hosts that were vulnerable. And most of them were really old software. Like people are still using a Netscape Enterprise server, which was discontinued more than 10 years ago. And a lot of people are using Red Hat versions that are discontinued for a long time and things like that. But this was the Züxel devices were the only ones we could identify which are still on the market. I tried to contact Züxel, I got no answer. So I tried to analyze their firmware. It seems they're using a custom TLS stack that is still vulnerable to this original padding oracle vulnerability. Okay, now we have the same error message, but then the next problem comes up, that's timing. So if you're checking this padding and checking the MAC, then checking a padding is much faster than checking a MAC, because a MAC involves a lot of calculations, some crypto, it's slower. So just by measuring how fast the server answers, we get a difference of these two errors again. So okay, we have the same weakness again, which was published a year later, also by Wardenay and some other people. Okay, so this must be fixed. TLS 1.2 says they knew about this attack and said, okay, in order to defend against this attack, implementations must ensure that the record processing time is essentially the same, whether or not the padding is correct. And then they propose some method how to do this, and then they say, okay, this leaves a small timing channel, but it is not believed to be large enough to be exploitable. Okay, so what TLS 1.2 says is you should fix timing, and they propose how you do it, and then they tell you, but it doesn't really fix it. Okay, and then some other things happened. SSH does something different. They are not using MAC then encrypt, they're using MAC and encrypt, which means they're calculating a MAC, then they are encrypting, and then they're putting the MAC of the unencrypted stuff at the end. And it turns out this can also be exploited. Then people from this university again found out that there's a very similar attack in XML encryption. So XML has an encryption mode, which is just not using any authentication at all. And it's not a padding oracle. What they're exploiting is a character encoding, but it's very similar. So you get a character encoding error in some situations, and you can use that also to decrypt data. And then you remember that I just said there was this small non-exploitable timing side channel. At least they thought it's not exploitable. Then some researchers came along and said, okay, we tried this and we can exploit it. The thing is, it's not a very practical attack. You need to be very near your attack target because it's a very small timing difference and you need to send a lot of packages so you can cancel out the noise. But still, it can be attacked. And what is really fascinating is how difficult it is to fix this properly. So you can build a TLS implementation that is timing safe against this attack. But for example, Amazon, they developed a TLS library and they implemented some countermeasures and that didn't work. So the authors of the Lucky 13 attack then looked at this and said, okay, we can break this again and called it the Lucky Microseconds attack. And then there are some implementations who are saying, okay, this is so complicated, we just won't bother with it. We will ignore it and just not fix it. And then that was just last week. Juraj Zomorowski, who is from this university, found out that OpenSSL, when they fixed the Lucky 13 attack, they introduced another padding oracle, which was based on the fact that they were not properly checking the length of the data. And which is more severe than the Lucky 13 attack because it's not based on timing. So it's really complicated inside TLS to properly fix this. Moxie Marlinspike has once said what he called the cryptographic doom principle, which is if you have to perform any cryptographic operation before verifying the MAC on a message you receive, it will somehow inevitably lead to doom. And he, in the blog post you can read he's describing the Wardenay attack and he's describing this SSH attack. So the idea is, okay, the very first thing you should do when you're getting encrypted data is checking that everything is correct by checking the MAC. So your protocol should be in a way that the MAC is protecting everything and the MAC is the very first thing you check. Because then there's no difference there are no different error states. There's just, when anything has been modified, you get an error. It's always the same kind of error and then you should be fine. Now, what people did especially when this Lucky 13 attack came out, and then they said, okay, there were so many attacks with these CBC modes, maybe we should get rid of it. And they look, okay, what else do we have? And there's one, and back then, most of the people were still using TLS 1.0. TLS 1.2 was available, but was not really implemented in widespread software. It was not implemented in the major browsers. So many people switched to RC4, and because it was just the only alternative available. Now, it was already known since the early 2000s that RC4 has some weaknesses, but nobody has yet exploited them in TLS. It was back then mostly interesting because it was breaking WEP, the Wi-Fi encryption standard, the first one. And what's happening there, so RC4 is not a block cipher, it's a stream cipher. So it's generating a stream of random looking bytes, and it turned out that at some bits, it's more likely that it's a 1 than a 0, or the other way around. At some bits, you have a bias that it's not really random, but some values are more likely than others. So this was known since 2000, and then like when people are moved to RC4, then some cryptographers said, oh no, that's not good. We know RC4 is not a very strong cipher. So they tried to attack it, and the first attack was in 2013. And then last year there was a bunch of attacks but all of them mostly just improved on the older attacks and just made them better and better. And the difference from this attack to the Lucky 13 attack is that there's nothing you can do in the implementation to fix it. It's just by design in the protocol, and without changing the protocol, there's nothing you can do against it. So, and this eventually led to an RFC that's now saying that RC4 is prohibited in TLS. And what you really should do is using what's called authenticated encryption. And the idea is, okay, we have these modes where people try to combine encryption and authentication, and everyone gets it wrong. Like, there are several different ways to do it, and most of them are wrong. And TLS got it wrong, and SSH got it wrong. And so let's have a standardized mode that's just combining encryption and authentication in one standard and in one operation. And for TLS, this essentially means using A as GCM. There's also another authenticated encryption mode, which is called CCM, but this is not widely used. So GCM is the one that people use today. And by now, most of the internet has moved to GCM. So if you have some modern server software and a modern browser, they will usually use GCM. And there's a new cipher, ChaCha20, in a mode called Poly1305, which is not yet standardized, but just a few days ago, there came an email that they now decided that they will standardize it, and it should be published pretty soon. So, yeah. And this is really something, like, if I should give a very simple advice for everyone implementing cryptography, is just always use authenticated encryption. This is not just a thing with TLS, but with all crypto protocols. If you use authenticated encryption, this would avoid all these padding oracle problems. Would also avoid these XML problems mentioned earlier. And recently there was an attack on iMessage, also because they were not using authenticated encryption. And that was myself that I showed that OwnCloud, they have an encryption module. They were not using any authentication at all, which meant you could mess with the files they were saving. Yeah, I think this is a straightforward and simple advice for all crypto designs. And I'm kind of wondering why people don't get this. Why aren't people following this advice? Like, this is relatively straightforward. You just have to look at one of these attacks. Like, look at this XML attack that was developed by people at this university. It's relatively easy to understand, and it's relatively obvious that this is the problem, and if you have authentication, you don't have this problem. So it should be a straightforward thing that everyone should know. And now I have to tell you a small story. Recently on some crypto party mailing list, someone sent a link to a script from a cryptography course from some university and said, yeah, this is a good introduction to crypto. And then I looked at it and wrote back, no, I don't think this is a good introduction. And the cipher modes that were taught in this crypto course were these 5: ECB, CBC, CFB, OFB, and CTR. Then recently on the RURSEC conference, I was sitting with some people, and I was saying, okay, I think many of these university courses are not very good. They're teaching outdated crypto and not non-practical crypto. And then, okay, I learned the person on the other side of the table was a professor teaching a crypto introduction course. I asked him, which cipher modes do you teach in your crypto introduction course? These 5 ciphers. And then I didn't exactly remember the ones, but later I checked and it were exactly the same. And then I Googled and looked for crypto introduction courses, and most of them are teaching these 5 ciphers. Some of them skip 1 or 2 or add 1, but this seems to be pretty standard. So I wonder, is there some list? Like, are these? Because it doesn't make a lot of sense. Like, we can go through them. ECB is not really a cipher mode. It's more an example what you should not do. It's the most naive thing to do, and it's completely insecure. CBC is the thing that brought us all these padding oracles. So maybe you should teach that, but only to attack it. CFB and OFB are pretty obscure things. You will not find a lot of protocols using them. So I don't see why people are teaching them. CTR is counter mode, which is the basis for also GCM, the standard modern cipher mode. So this may make some sense. So yeah, I wondered why these 5 ciphers. And then I had an idea. Do you know this book? It's Applied Cryptography from Bruce Schneier from 1996. Now, I mean, this definitely was a very influential book for cryptography, but it was 1996. And I mean, we moved on. We have newer research, we have better cipher modes, we know things that we didn't know back then. So, yeah, maybe this is the problem, that people are still learning crypto based on this book from 1996. Because, I mean, the padding oracle attack was in 2002. Bruce Schneier couldn't know about this. He couldn't know about these XML attacks and these SSH attacks. But today we know this, and today we have authenticated encryption modes. Yeah. And I checked at the Ruhr University, the crypto introduction course in the last semester. They have these cipher modes. It's the same list, just one. They skip CFB, but yeah. So, yeah. Maybe this is a problem. Authenticated encryption, so generally it's a solid advice if you do anything with crypto, use authenticated encryption modes wherever you can. And today the standardized modes are GCM and Poly 1305. But this isn't the end of the debate. So there's quite some skepticism, especially about GCM. That people say, okay, it's secure if you implement it properly, but there are a lot of timing issues if you don't implement it properly, and there are a lot of things you can get wrong. So it's better than inventing your own combination of CBC and HMAC, but it's maybe not the end of the debate. And there's currently a competition for new authenticated encryption modes, the CESAR competition. And there's an idea called synthetic IOVs, because one problem, yeah, I come to this on the next slide. GCM needs a nonce, and nonce means number used once. So for the same key, you can never use the same nonce again. And there's a similar problem with other authenticated encryption modes, but with GCM it's especially devastating. Because if you use the same nonce twice with the same key, then everything falls apart. Then you lose your authentication, then the authentication key can be practically broken just if you have two nonces that are the same. And there are implementations that are doing this, and I'm currently with some people working on a paper on that, which will be published soon. Okay, now I come to a bit of a different topic, that are TLS implementation bugs, and also bugs that are not necessarily security issues, but that indirectly can cause security problems. And this story starts in 2008, where I opened a bug at Mozilla. And what happened was that sometimes I was calling my own web page and I got a wrong certificate. I got the default certificate from the server and not the certificate from my web page. And why was that happening? I first didn't understand it, but yeah. And to understand this, you have to understand something about the different TLS versions. So the first thing that happens if you do a TLS connection is, like, the client says something, dear server, I support these versions of SSL and TLS. And it's like you say a lower version and lowest version and the highest version. And then the server says, okay, I support this version. So because if you have a new version, like sometime next year we will have TLS 1.3, and there will be some servers that don't support it, of course. So a client will say, okay, I can connect between TLS 1.0 and 1.3, and then the server might say, okay, I only support TLS 1.2. That's fine. Now, there's a problem that there are some servers who, if you send them, oh, I want to connect with TLS 1.2, they say, oh, no, they don't say anything, because they say, okay, here's something that I don't know about. I will just not connect with this. I will not send any error or anything, just ignore it. This is called version intolerance. So, for example, you probably know this SSL Labs test, where you can test how good the configuration of some server is. and it says it will tell you if a server has this problem. And this is always a bug. So this is not not properly implemented TLS implementation. It's always the bug on the server side. But then the browsers knew about this and saw a problem that they couldn't connect to certain web pages due to this bug when they introduced newer TLS versions, and they implemented a fallback. So a browser first tries to connect with the highest version and lowest version it supports, which at the time was SSL3 and TLS 1.2. No answer, okay, then the browser tries again with a lower version. It tries again and again and again till the oldest version it supports. Has also been called a protocol dance later. And you might wonder, can this be a security problem? Because what an attacker can do is just blocking the first connections, and by that downgrading you to an older version. And maybe this older version has a weakness and you're not profiting from the security improvements from the newer versions. But this was also what was happening with my bug report, because what I was using was a thing called SNI. It's a TLS extension when you have one server with one IP and different host names, because the original SSL didn't have a concept of host names, so you needed one certificate for every IP. And then there was an extension that allowed that you could say, okay, I want a certificate for this host name, and you could have different certificates. But this was only introduced in TLS 1.0. So when there was a downgrade to SSL version 3, which can also just happen because of a bad internet connection, then you got the wrong certificate because this extension was not supported. Okay, I finally kind of fixed this by disabling SSL version 3 on my server, so the browser could no longer downgrade to that. But yeah. And then at the Black Hat conference in 2014, Antoine Delina-Lavou presented something he called the virtual host confusion attack, which was a relatively obscure, complicated attack, but interesting thing for me is that he described this protocol downgrades, and he said, oh, it turns out it can also be taken advantage of by a network attacker to exploit virtual host confusion. So yeah, it is a security problem. The thing was, this attack a lot of circumstances had to be true that you could exploit this attack, so it didn't get a lot of publicity. But then later that year, Poodle came. Poodle was another padding oracle, which is based on a different mechanism, because the old SSL3 protocol does not define how your padding bytes have to be. They can be random bytes or whatever, and that can be exploited. So it only works against SSL version 3. So you should say, okay, no problem. We're all using TLS 1.2. Nobody cares if SSL version 3 is broken. But we have these downgrades. So the attacker can just block all the connections with the newer TLS versions and force a connection with SSL version 3 and can then launch this Poodle attack. The solution for that was that a new TLS extension was introduced called SCSV, where a server can tell the browser, I'm not broken. If I really mean it with the version that I'm telling you, and you don't have to do these downgrades with me. So you really have to appreciate what's happening here. Like, okay, we have a working version negotiation mechanism. Then we have servers that implement it wrong. Then browsers implement a workaround. Then this workaround creates a security problem. So we need another workaround for the security problem caused by the workaround for a bug. And that's a new standard. I mean, these downgrades never were standard. So yeah. Actually, it turned out that it doesn't have a lot of practical relevance today, because at some point the browsers decided maybe we can just disable these strange downgrades and it won't matter that much because most servers have been upgraded by now, and that's what happened. So as far as I'm aware, I think Mozilla has disabled all these downgrades and Chrome is currently in the process of doing so. This is not the only time something like this has happened. At some point, people found out that some load balancers from company F5 had a problem if you sent a TLS handshake with a certain size, between 256 and 512 bytes. So it just didn't answer if you tried a handshake with that. And people were adding new features to TLS, so the handshake got bigger, and at some point it grew larger than 256 bytes. So what do? We introduce a new extension, a padding extension, so we can pad our handshake. This extension does nothing, just adding some bytes. So we can make it bigger than 512 bytes to work around these broken load balancers. Next thing that happened was that people found out, okay, there are other broken implementations that have a problem if the handshake is larger than 512 bytes. Interestingly, these are mostly used for email, and the others are mostly used for web. So you can kind of choose, you enable the extension for web and disable it for email, and then this kind of works. But yeah, it shows a bit how messed up the situation sometimes is. Okay, so now a completely different topic. Cryptography is based on mathematics. So when we make some security assumptions, we usually assume that the mathematics is correct, like we don't have calculation errors. But what happens if it's not correct? This catched my interest. There was a bug in OpenSSL that the BN square function produced wrong results in some very rare cases. And so it was like 1 out of 2 to the power of 128 cases, which is so rare that you cannot hit it by chance. The OpenSSL people spent quite some time to check if this is exploitable. They found nothing. And the reason for that is that they didn't use this function very much. But it was an interesting bug. And then I told you earlier that I usually do fuzzing. So I thought, okay, can we use fuzzing to find these kinds of bugs? And already Ralf Philipp Weinmann had a talk at Black Hat last year where he analyzed this bug, and he used American Fuzzy Lob, which is a very advanced fuzzing tool, and he was able to rediscover this bug with this fuzzing tool. And I did the same, like I used fuzzing to test math implementations, and what I did is what's called differential testing. I'm using 2 different implementations from the same functionality, and then I'm comparing the result, and then I'm just using random inputs and let the fuzzing tool generate these random inputs. Because if you have something like a multiplication, there's just one correct result. If you have 2 different results, something is wrong. Like, at least with discrete numbers, there's no doubt that they must be identical. And this was quite productive, so I found a bug in OpenSSL in the bnmod_exp function, which is used for RSA and Diffie-Hellman. Interestingly, nobody found a way to exploit this yet. I would be very interested if it's possible. I know a number of people have looked at it, but then in basically the same functionality in NSS, there also was a bug. In the elliptic curve implementation from Nettle, and quite recently in the poly 1305 function in OpenSSL. What these usually are carry propagation bugs. So what you're doing, if you're doing something like a multiplication, you're doing it in a small variable, and if there's an overflow, then you have to add something to the next variable. And this is quite error prone. Yeah. So some other implementation issues that come up. One interesting thing is that Bleichenbacher developed 2 very popular attacks. You should not mix them. One is against RSA signatures and the other against RSA encryption. This one is against signatures, and the thing is, inside the RSA function, you're using a very specific structure, and if the parsing of that structure is ignoring some bytes at the end of your signature, then you can exploit this attack. And a variation of this attack was the Berserk attack, which involved ASN1 encoding, which is a very weird encoding standard that's used everywhere in crypto. then people just don't check certain things. So I said earlier that the poodle attack was possible because the padding in these old SSL versions was not defined. Now in the TLS 1.0 and later, the padding is defined. We had it earlier, like the padding is always this number and then number of bytes. But if implementations don't check this, this attack gets possible again. And that's Adam Langley found that there are a number of implementations that just don't check these padding bytes. Then there are implementations that only check some of the padding bytes. And there was also a very interesting one. I figured out that I found that in GNU TLS, it was not checking the first padding byte. And then I talked to Juraj about this, and he said he has heard about this before, and said there was something about it in the Lucky 13 paper. And then I looked it up, and in the Lucky 13 paper, they actually said it's missing 1 byte of the padding check. But it was actually that it was missing 2 bytes of the padding check. So they fixed it, like checking 1 byte more, but still missing 1 byte. Yeah, and then some implementations just don't check the authentication MAC. Like they don't check the authenticity at all. And there's also a thing called the finished message in TLS, which is kind of protecting the whole handshake and making sure that both partners saw the same thing. And there were also implementations that didn't check this. All these kind of bugs made me say, okay, it's pretty much you can imagine any kind of implementation error in TLS, and you will almost certainly find it in the wild. And the nice thing is today we have these possibilities to do internet-wide scans that we're just scanning all valid IPv4 addresses. And you will find something that's vulnerable if you can scan for it. Almost all the time. One thing about when we find out that these old versions of the protocol have weaknesses, then we would like to deprecate them. We would like to disable them. We deprecated SSL version 2, version 3 in the past, RC4 and SHA-1 signatures, and we learned that it's very painful. And the reason is that there are a lot of devices out there that only support these old methods, and we don't want to lock people out from our services, and especially the SHA-1 deprecation has caused a lot of debates about some companies saying we still need to support this because there are people with old mobile phones that cannot connect with anything else. And one problem here is when in 2010, Microsoft produced a very expensive phone together with Nokia, which is using Windows, mobile, whatever. And they have a mail client that only supports SSL version 3. Now, SSL version 3 is from, I think, 1996. And in 1999, we had TLS 1.0. So this was already like 10 years behind the standard. And then Poodle came, and people said, okay, SSL 3 is broken, we need to disable it. And mail providers disabled it. And people were left with their very expensive phones that were just a couple of years old, and they could not check their emails anymore. And Microsoft didn't bother to fix it. And I think this is really annoying, because basically they shipped a product with substandard security and really, really very old deprecated encryption. And the same thing is happening today. I mean, we know that all these padding oracles, that's really ugly and hard to fix, and maybe we would like to deprecate that as well. But there are companies like Apple. If you have Apple Mail, then it will only use TLS 1.0. That means it will use all these modes that are vulnerable to all these padding oracles. So deprecating that will be hard. There are probably a lot of other products only using TLS 1.0, but Apple is probably the most prominent one. And I don't know how to change this. We should put more pressure on these companies that if you deliver a new product, it should have up-to-date cryptography. It should not have deprecated 10-year-old cryptography. Okay, then I want to say something a bit more general for the end. There's a tendency to make TLS the default, especially in the web. So Google is pushing for this in Mozilla, and there's Let's Encrypt, which is issuing free certificates to make it easier to get HTTPS. And I think this is a very good thing. And I think everyone should obviously agree because it's more security, it's a good thing. But there's a surprising pushback against this. So especially if I read online discussions like on Hacker News or Heise or Golem, whatever, I see a lot of people don't like this and say these bad companies forced us to use encryption and we don't want that. And I think a lot of that is based on misunderstandings. This is the most common one I hear, that people say, oh, I don't need this because there's just nothing secret on my web page. And this is missing an important point, that TLS is not just about encryption, but it's also about authentication. So you're getting a guarantee that people cannot read your data, but you're also getting a guarantee that the data is not modified. The example on the left is from a supermarket in Copenhagen, actually. And the banner here is from the supermarket. So they have a free Wi-Fi in the supermarket, and they inject their banners into web pages. So maybe you don't want other people to have banners on your web pages or replace your banners, which is all happening. This is at Brussels train station. This is in the New York Times. This is not from the New York Times. This is from the Wi-Fi. So they are adding some where you can get some information about the Wi-Fi. But there are also like, if people, for example, software web pages, if you're providing a software for download, a lot of software web pages are not HTTPS. And then it becomes a severe security problem. Like you're downloading a software unencrypted, and then you're running the code. So it should be obvious that this should be encrypted. But I'm having a lot of debates about these kinds of things. Then people have the idea, okay, we will only encrypt the secret data. For example, this is GMX. GMX, the large German email provider. It's not HTTPS. Here's the login. But if you log in, the login data is sent over HTTPS. This is completely insecure because the attacker can just change the login form to send the username and password to the attacker website and then forward it back to GMX, and the victim doesn't notice it. This is called an SSL stripping attack, which was, I think, in 2009 presented by Moxie Marlinspike. Then people have very wrong ideas about performance in crypto. People say, oh, it's so slow and my server will have such a high server load, I cannot possibly do this. And usually if people say this, they have never done a benchmark on it because it's hardly measurable. So people think, okay, crypto, this is complicated math, it must cost a lot of performance, but that's actually not the case. Crypto is really, really fast. And for most standard scenarios, like you have a web server which is running PHP, you will hardly be able to measure the actual performance hit by TLS compared to what your PHP interpreter is using for performance. So usually this is just irrelevant. This matters if you're Cloudflare or some other large company that's serving millions of web pages. And then you have to worry like if you want to use some different algorithms, but usually it's just not a big deal. And then there's quite some debate about certificate authorities. So people say, okay, these certificate authorities, that's all a corrupt system. And this is in part true. So there have been a lot of problems with certificate authorities. The basic problem is we have a couple of hundred certificate authorities, and all of them are kind of on the same level. So if you have a web page, every of these certificate authorities can issue a certificate for you. And how trustworthy are these? What kind of companies are they? Yeah, there have been quite a number of attacks. But the situation is definitely improving here. What we have now is a CA browser forum, which is defining guidelines how these CAs have to operate, which is a huge improvement because in the past they could just do what they want. They were doing things like selling boxes that were intercepting traffic by generating valid certificates on the fly. which is today we have a clear guideline that this is forbidden and you're not allowed to do this. And we have new technologies to prevent problems. There's one new standard called HTTP public key pinning, where a web page can tell the browser that please save my certificate and or a hash of my certificate and save a hash of a backup certificate, and only these certificates are allowed for this web page. This adds an additional layer of protection where you don't have to fully trust your certificate authority anymore. As soon as a user has visited your web page once, you have this additional protection mechanism and don't have to trust them anymore. A problem with that is if you lose your certificate and key and also your backup key, then you have a problem, because then then people can no longer serve to your web page. So this is a very strong security mechanism, but it's dangerous. You should only use it if you really know what you're doing. And what is a bit worrying, recently Netcraft had an article where they did statistics on HPKP, and they found out that I think about a third of the headers they saw in the wild were somehow malformed. They were pinning certificates that they were not really using, or they were just pinning one certificate which is invalid or somehow. So it seems people are using this without really understanding what they're doing, and this is a bit worrying. And then there's a project from Google called Certificate Transparency, and I think this is the most promising technology to make certificates more secure. And the idea is to have something which is a bit like Bitcoin, that you have an append-only lock, which is a public lock where everyone can look what's in there, and every certificate is supposed to be in this public lock. Right now, this is only enforced for so-called extended validation certificates, but the idea is on the long term, all certificates should be in this lock. And this already found a number of issues. There's now a web page where you can see when where you can check all the certificates in the lock for certain errors. Like most of them are minor things, like there's some encoding error, but there's a rule that you're not allowed to do this. But there was also one case where Symantec, they issued certificates for Google and a number of other big web pages, and Google didn't know about this, and they found these certificates in the lock. Yeah, so it works. It really finds real problems. And I think this is making this system much stronger and should make these concerns about this CA system. I mean, you can still be concerned about it, but it's much less of a problem than it was a couple of years ago. Then the real problem many people who would like to move to HTTPS have is third-party content. So if you have a HTTPS web page, also all your JavaScript and your banners and CSS and videos, everything must be HTTPS as well. And many people use content outside of their control. Like they're embedding some video, and the major thing is they're embedding advertisement. And this is already by itself a security problem, because you're executing code in your web page that you basically have no control over. And ad networks are not very well audited and checked what kind of code is in there. But this also prevents a lot of people from switching to HTTPS, especially media web pages. So I know that a lot of media web pages, and I know it myself, like every time I write an article on Golem about HTTPS, there's a comment, why is Golem not available over HTTPS? And this is the answer. Like, we have advertisement, and that's how we get paid, and we have little influence to change this, unfortunately. Small look into the future. TLS 1.3 in the next version is coming, and it will deprecate a lot of things that are problematic. So it will deprecate the RSA handshake, which is the reason for all these Bleichenbacher attacks, like Drown. It will deprecate all unauthenticated encryption modes and all this CBC HMAC stuff and Magnet encrypt. So all the sources of these padding oracle vulnerabilities will be deprecated. It will also deprecate the old version of RSA. So there are two different standards how to do RSA. and it will deprecate weak hash functions. So a lot of these problems should no longer appear. Some problems, I kind of expect that we will see this version intolerance problem again. We will probably find out that some servers now accept a TLS 1.2 handshake, but will have a problem again if you try a TLS 1.3 handshake. I don't know if anyone has done an internet-wide scan on this yet. Would be very interesting. And another aspect is even if you have this new protocol which doesn't have a lot of these problems, and if you have still these old protocols around, there may be cross-protocol attacks, which was also a paper from Bochum last year, where they said even if you have TLS 1.3 and you have a Bleichenbacher vulnerability in your TLS 1.0, then you can use this to make an attack on the new protocol. So, and there's this deprecation concern, like it's hard to deprecate these old protocols. So TLS 1.3 will solve a lot of problems, but not all of them. So conclusions, yeah, TLS is becoming the default, which is a good thing. I think we should push that. There's a lot more research in recent years, and old attacks are coming back. We should look at old attacks and re-investigate them. And we need better testing for these implementation errors that cause trouble. Yeah, thanks for listening. I hope you have a lot of questions and we can have a nice debate. Yeah.